1. Now we will see how Python reads a WAV file. All computer files are binary data that is made of zeros and ones. However, we always deal with bytes, which are the smallest addressable group, and they are 8 bits in length. A byte can hold 256 values, which is 2 to the power of 8. 2. A stereo WAV file consists of 2 channels, left and right. Each channel sample is of 16-bit length. A 16-bit number can represent 65,536 values, 2 to the power of 16. A signed 16-bit integer can represent anything from -32,768 to +32,767. 3. Now we will calculate the size of a 1-minute mono WAV file. In a mono WAV file, there are 44,100 samples per second. This rate is based on the Nyquist theorem, which states that to retain the frequency f, we should sample at a rate of 2f. Thus 44,100 sample rate should be able to reconstruct audio data for frequencies until 22,050 Hz. There are 44,100 samples per second, and since each sample is 2 bytes, we have 88,200 bytes per second. If we multiply this number by 60 seconds, we get 5,292,000 bytes. The actual WAV file size is 5,292,044. We always have to include a 44-byte header. The header will have some identifying information, and also information about the kind of audio signal. 4. Likewise, the data size for a 1-minute stereo file is double the number above, and we have 10,584,000 bytes. Again, the actual size of the WAV file is 10,584,044 bytes, resulting from the 44-byte header. 5. Most audio is not stored as WAV, but compressed formats to save disk space. However, to do audio analysis, we need the WAV format. Likewise, after audio synthesis, we will write to the WAV format. 6. As mentioned, the WAV file has 44-byte header. The information in the header is thoroughly documented on the internet, and you could search for the specs. Now 2 methods of reading WAV files are discussed. The first method is important to understand how Python deals with files. It is also helpful in understanding the structure of bysynth file. The second method is the recommended way, and is more abstract in that it hides the details. Furthermore, it is more efficient. 7. To read a file in Python, we have to use the open command. The open command needs 2 arguments. One is the file name, and the other is mode. The 2 modes for WAV files are RB and WB for reading and writing binary files. Whenever you read a byte in Python, a string is returned from \0 to \0xff. \0x is the standard way of declaring something as hexadecimal in Python. The hex values are 0 to 9. And a 2f, the letters can be either lowercase or capital. 8. This is an example of a string that might be returned by reading the binary file. We can see the string contains 4 hex digits, 2 bytes, or 16 bits. We can decode this to a number between -32,768 and +32,767. 9. The string is read as FEFD. The reason we read it this way is because of the little endian format. In the little endian format, the second address is more significant for a 16-bit integer. Basically, it means that we reverse the string bytes. In the string, FD comes first, and FE is second. However, we read it as the reverse for the conversions. Most computers are of little endian format. FEFD can be represented as a 16-bit binary number. Since it starts with 1 leftmost bit, the number is negative. The first bit is always the signed bit inside representations. The absolute value can be obtained by the 2's complement, inverting all bits, and then adding 1. The 2's complement gives an absolute value of 259. Thus the number is actually minus 259. 10. Rather than deal with all this math, we can let the computer figure it out. We input the string to an unpack instruction. We have to tell the unpack function we want it to treat the string as signed 16-bit integer, which is the H flag. All the different flags can be found in the documentation. The unpack function in struct module results in a tuple which can be thought as a set of numbers. Our set is just one number. We will go over tuple and other data structures in detail later. Then I extract the 0th element, which is the only element. I write _3 to get out 3 variable. 11. In the second example, a positive number is in the binary string. The hex is 1405, which is just the reverse of the string. If 1405 hex is written as binary, we can see the leftmost bit is 0, and thus the number is positive, and value is 5125. 12. We can verify, with Python code, that indeed 5125 is the value of string. 13. I have a test file called wavered.py which I will upload to pythonaudio.blogspot.com. To understand this file, we have to understand how we can read a 2-byte number or 4-byte number using the read instruction. The data is signed. However, everything else is treated as unsigned, and the format flags are capital H for 2-byte integers and capital I for 4-byte integer. A lot of headers are ASCII text codes, and unpacking is not necessary for them, as print can easily deal with them. 14. This is the output of wavered.py file. It reads the header and all values are consistent with the mono signal. It also reads the first 5 samples. If we were to read the stereo file, each sample would correspond to 4 bytes, 2 bytes for left and 2 bytes for right channel. Now the correct formatting flag is HH to indicate 2 separate 2-byte signed numbers. 15. From the header we can find the data size and also the byte rate. By dividing the 2 numbers we can find how many seconds are in the WAV file. 16. This is the other way of reading a standard WAV file. It imports IO WAV file submodule from the scipy module. By using the read function inside the submodule, we can read a binary file. This is more abstract and is more efficient. Next, I extract 5 elements from the data using slicing, the basic extraction method in Python. 17. The reason I spent so much time on details of struct is so it's easier to understand by synth, which uses that function. It also uses another module called wave, which makes reading WAV files easier than using Python open command. This hides more details of the header, as can be seen next. 18. The struct module is used to read a few data values. I show the commands to read the first 2 samples. 19. This shows the first 5 samples. 20. In Bysynth, most of the time is spent on writing WAV files. To understand writing of WAV files, it helps understanding how WAV files are read, and then using the set and write functions in the documentation, we can write a WAV file. 21. This is how you get documentation on the WAV module, which will give more information about the set and write commands. 22. You may go to pythonaudio.blogspot.com to see the slides. To see a larger image of the slide, you can click on them at that page, which provides easy navigation controls. The text for the audio of the slides as well, as any relevant source code is also on that page.